great pleasure of having Vincent Vargas from Genève, and he's going to tell us about conformal bootstrap in Liouville theory. Thank you, Vincent.
Okay, so thank you for the invitation. I was talking in Vienna 2 days ago. I mean, it's incredible now with this Zoom thing that we're talking all over the planet the same week. But okay, hopefully we will meet again someday. What I'm going to discuss is what has been put on archive right now, and it's it's kind of this endless project we've been having for years, and hopefully it'll be completely settled within a few weeks on archive. We're still looking at the last details. So I'm not going to discuss what we're doing right now. I'm only going to discuss what we have put on archive, because I have to do lots of introductions. So this program is something we started with Kupiainen and Rhodes, and we were joined in the middle of the program by Guillarmou, who is a specialist of spectral theory, and so he has been tremendously useful in what we're trying to do. As you'll see at the end of this talk, there'll be some spectral theory involved. Okay, so let me give you the context. So general context is that, okay, so Liouville is a special quantum field theory, but more generally, quantum field theories are important because they model statistical physics, and also maybe even more importantly because they are used to describe nuclear physics, like for the Yang-Mills and all that. And when you look at a quantum field theory, usually you have some kind of underlying field in your theory, and what you're interested in, what has the physical content, is the correlation functions, where you roughly take your field at different points in space-time. So what we're going to discuss today is 2D space-time, but okay, the most interesting quantum field theories are usually in 4D space-time. So what you're interested in is you take different points in space-time, and you take your field at these points, and you look at the product, and you take some kind of average, and that's what are called correlation functions. And when you look at certain statistical physics models at critical temperature, they're expected to exhibit conformal symmetries, and they are thus called conformal field theories. And this is true in dimension 2, but also 3, for instance. I mean, there's not, though in dimension 2, there has been much more work on conformal field theories. And so in 1984, Belavin-Polyakov-Zamolodchikov, they observed that when you look at correlation functions that you impose certain symmetries, then it gives you strong constraints on the system. And so they did this in dimension 2. And so they realized that in dimension 2, when you have conformal symmetry, you have essentially one parameter called the central charge, which classifies what your conformal field theory looks at. Okay, so I'll be more precise in a few slides. And doing that, they were able to construct lots of conformal field theories, among which the critical 2D Ising model, what are called minimal models, etc. And so their approach was not at all based on some kind of underlying path integral or probabilistic measure. They were using some kind of a general scheme, which was based on representation theory, what is called representation of the Virasoro algebra. And so basically, just to say it right now, our goal is on one special conformal field theory called Liouville, which we constructed some years ago using probability theory. Our goal is to recover the conformal bootstrap construction of Liouville. So I'll be more precise a bit later. Let me finish by saying that these ideas of looking at correlation functions with conformal symmetry and trying to understand them, classify them, has known a huge success recently in 3D, where they realize that in these dimensions, conformal symmetry also constrain the system a lot. And so they're able to classify conformal field theories, and in particular to have very, very spectacular numerical predictions for the 3D Ising model at critical temperature. So I mean, I always mention this because I guess this is the future of conformal field theory, and maybe hopefully while we're all still alive, we'll see progress in understanding these conformal bootstraps in dimension 3. But okay, right now, most progress is restricted to dimension 2 in probability theory, in understanding conformal symmetry. Okay, and so let me stay with a general slide. So as I said, so on one, there are kind of two approaches to quantum field theory, conformal field theory. On one side, you have axiomatics, constructions, definitions. So you set a bunch of axioms and you say, okay, my conformal field theory or my quantum field theory, it has to satisfy axioms, you know, typically gluing axioms, like you want to define your theory on a Riemann surface. Well, you prescribe how it behaves when you cut your Riemann surface and you glue it back together. So these are called Seagal's axioms for conformal field theory. And you also have other axioms, the OS axioms, etc. And you have these axiomatic constructions, which are the conformal bootstrap. And so in math, you know, it's kind of hard to make sense of these axioms. And there's an approach which is called the Vertex Operator algebras. And but I mean, right now, I'm putting that on a general rigorous footing is difficult. And for instance, in the case of the conformal field theory we're interested, Liouville, all these approaches, vertex operator algebras, they're inefficient because you have to handle an infinite number of representations. So it's right now it's inefficient for our purposes. So on one side you have the axioms in quantum field theory, and on the other side you have a more constructive approach, which is based on these path integrals. And this is where probability comes into play, because thanks to the Gaussian free field, essentially, so we can try to make sense of these path integrals in probability theory. And so, for instance, I mean, it was probability theory in the 50s and the 60s, you know, where we defined, I mean, where people studied Brownian motion. And so Brownian motion is essential when you want to define one-dimensional path integrals, where space-time is one-dimensional. And so, but you can also use probability theory to try to make sense of these path integrals in higher dimension, in which case things are a bit more tricky, because the underlying field you're going to use is the Gaussian free field. And so in dimension 1, the Gaussian free field is Brownian motion, but Brownian motion is rather nice because it's a continuous function. Starting in dimension 2, it's no longer a function, the Gaussian free field. So you face quickly renormalization issues when you want to define these path integrals. But nonetheless, I mean, let me say that once you have defined these path integrals, it's not at all obvious that you can recover the other approaches to the theory. And so that's what we're going to do in Liouville.
So just trying to understand better. So when physicists consider the axiomatic construction, do they care at all about, I don't know, existence of a theory that, I mean, do they try to prove existence of a theory that satisfies the axioms? Do they have questions about uniqueness, or is it just...
yeah, so okay, so that's, yes, I mean, the point is, okay, I'm going to give you the example of Liouville, because I mean, in the case of Liouville, when you apply the conformal bootstrap, there's no guarantee that you get something which is meaningful, because the point is when you have gluing axioms basically, and it's very hard to show that they're consistent. I mean, there's no proof of, except, okay, it's a byproduct of what we did right now, but before that there was no proof that the construction of Liouville really existed, because I'm going to go in more detail in a minute, but there was no proof that some objects converge, for instance. Okay, and so but physicists use numerics. And actually, I mean, in 3D Rychkov, it's the same thing. They use numerics. They don't know what the real numbers are behind the, you know, the correlations, etc. They have, I mean, it's all based on numerics right now. But, and so it's waiting for a clean mathematical, definition. Okay, so as I say, from 2 to 1 in the context of Liouville theory. So I'm going to go in more detail. I mean, it's very hard. I mean, this is a very general picture, but it's good to have a precise example, and that's what I'm going to give you during this whole talk. I mean, a very special example that we worked out from, you know, A to Z. I mean, we completely worked out this example, so we're kind of happy because we have an example where we can really construct an object, you know, quantum field theory using probability and completely relate it to all the axioms that are written in physics. Okay, so it's kind of a you know, a test for these ideas that we managed to work out. Okay, so roughly there are 2 axioms when you do a CFT. So the first thing is, so as I said, you have a bunch of fields which are indexed by alpha. So alpha is, you know, it can be a finite number of fields like in Ising, it can be an infinite number of fields like in Liouville, but you have an infinite number, you have fields which are defined at points now I'm talking in 2D. From now on, everything is restricted to 2D. So they're indexed by Z. So you have to see this as random generalized function on the complex plane. And when you look at these fields at different points, you compute the correlations. Then what happens when you apply a Möbius transform on the sphere? So it's the, you know, the only it's the conformal maps from the Riemann sphere to the Riemann sphere. What happens is that your fields, your correlations, they move like tensors. So you get the same thing up to the product of powers of psi to some psi prime to some power. Sorry, and these powers are called conformal weights. So basically, when this is the first axiom of a 2D conformal field theory. It's now, if you look at this, you take little n equal 3. Well, when you're on the Riemann sphere, there's a unique Möbius transform which sends any 3 points on the sphere to any 3 other points. So if you exploit this thing, then you can show, it's not very difficult to show, that this relation completely characterizes the 3-point correlation function of your random fields. Okay, it means that if you fix Z1, Z2, Z3, well, it's some kind of, you know, differences of the points at certain powers times a constant, which depends on the index alpha 1, alpha 2, alpha 3. Here there's a typo, of course, it's alpha 3, V alpha 3. Okay, and this constant is called the structure constant, and it's essential. And so in Liouville theory and the bootstrap approach, the axiomatic approach, they set this constant to satisfy some kind of, you know, intriguing formula called the DOZZ formula. So first step in the bootstrap is 3-point correlation function. It's explicit up to a constant, and this constant, well, we have to guess. So here's where the black magic enters. I mean, they tried to guess these constants. Okay, so you can see this as the correlation function when you take Z1 equals 0, Z2 equal 1, Z3 equal infinity. So sometimes I'll use this notation too. Okay, second axiom, so it's kind of sketchy, is once you know what the 3-point correlation function of your theory is, you want to know what is the 4-point correlation function. And then the 5-point, etc. So you need some kind of recursive rule. So this is what is called, you know, this is when you really, so last time I think, and I was in Rio, I think I did the talk on DOZZ, and so this talk is more about the sequel. And the sequel is, you need, when you want to construct a 4-point correlation function, you need to prescribe how you can recover it from the 3-point. So what you do, I mean, what they assume, and this is old stuff. I mean, it goes back, I think, to Wilson. You say that, for instance, I want to take a 4-point correlation function. So what I do is I gather the two first fields together, and I write some kind of expansion. So this is kind of non-rigorous at this stage. But what they do is they postulate that you can decompose the product of your two fields as a sum over some fields, and times differential operators, and which will depend on the index alpha of your basis, and on the alpha 1, alpha 2 here. And what they do is they plug this kind of series expansion on differential operators into their 4-point correlation, and then they end up with applying differential operators on 3-point correlation functions. So imagine here you just have one extra field, V alpha 4, Z4, then you see you apply differential operator at a 3-point correlation function. And then you sum this stuff and you get an answer. Now the question is, what is this procedure? Now when you do, and this is I guess this is what discovered BPZ, Belavin-Polyakov-Zamolodchikov, is that if when you start to write that these correlation functions have to have conformal symmetry, then the differential operators you get, well, they're the structure constants times some kind of infinite series, which is non-explicit, okay, and which is supposed to depend only on what is called the central charge of your theory. So it doesn't depend on 3-point correlation function. And so the second main tool to understand a conformal field theory is to understand the indexing set here as the basis of your development, and this is called the spectrum. Okay, and so as I say, you iterate what is called this operator product expansion, and you get the 4-point, the 5-point, the 6-point, etc. And here is to answer the question of Hubert, is that when you do this, there's no reason this sum converges. Okay, you have, in the case of Liouville, it was an open question, and also, so this is a very important point, is that when you do your asymptotic expansion, you make Z1, Z2 the difference go to 0 in this kind of procedure, but you can also, well, try to make Z1 minus Z3 go to 0. You could, expand the product of two different fields, and you'll get a different answer, but it has to be the same. So it gives you a constraint on your system, and this is what they use in the Bootstrap procedure. It's kind of like when you have a function of several variables. I mean, if you do a series expansion along two variables or along other variables, you're going to get different answers seamless, but if you're starting with the same function, it has to be the same thing. So, okay, what you have to understand is that what you do here is you can do it with different points and give you lots of different ways of constructing correlations, and they have to all be equivalent. And this is what is called crossing symmetry constraint, and this is what physicists usually justify by numerics. Now, what makes Liouville a bit difficult is that this sum is not a sum, in fact, because the spectrum is a continuum. So the spectrum is a parameter capital Q plus I times the positive line, and the sum is an integral. So, and we'll see in a moment what capital Q here is. Okay.
So yeah,
so this was
Vincent. So the Z they live in C, and this has to be, this is a toy for space, a toy model for space time, right? Yeah. What is there any easy, understandable interpretation for the alphas? What do they stand for?
The V alphas.
Yes, the space in which they live. What does it correspond to?
So V alpha is real valued. It's a random distribution.
No. I'm talking about alpha.
The alphas.
The alphas, not the
that's
alphas.
The point. I mean, it's kind of a guess. For Ising, alpha it has cardinal 3. So in Ising, you have the spin field, you have the energy density, and you have the trivial field 1. And so if I do the bootstrap for Ising 2D, I'm going to write that V alpha 1, V alpha 2, it's the sum over 3 terms. I mean, but this is something you physicists kind of guess. I mean, I don't really know how they do that. I mean, they have procedures.
Okay. So it's a space of parameter that makes things work.
Yeah, but in fact, sometimes, I mean, physicists look for the highest possible spectrum. I mean, for instance, I don't think it's known for CLE. If you want to construct a conformal field theory out of CLE, what is the alpha? What is the spectrum of CLE? I don't know if they know that right now, because you have a bunch of fields, but you can have even more fields you didn't think about, etc., etc. So it's, for instance, okay, this is I think a good question I'll talk about at the end. But what is the spectrum of CLE? Okay. Okay, so here's the plan. So I'm going to give recall the probabilistic construction, then give the main result, and then, if I have time, the strategy of proof and perspectives. But first, let me first now jump into the path integral of Liouville. So it's always delicate because I have to I mean, our program is going forward, but at the same time, I always have to recall all the basis of the probabilistic construction. But here I'll be kind of sketchy, so I have a bit of time for the rest. So what is Liouville? So Liouville is the path integral where you reweight the uniform measure on the space of maps by the action. And the action is what? Is I take the gradient of my field squared, which is the standard quadratic action, which produces the Gaussian free field theory, plus a harmless term, which is linear in my field, which is 2q, the field which I integrate against the background metric. So for me, I'm throwing away Riemannian geometry right now, so everyone's comfortable, because so the background metric is just some function which decays like 1 over z to the power 4 when z goes to infinity, and plus the interesting term, which is the interaction term. So we reweight by these two terms plus the exponential of my field, and there's a special relation between gamma and q, and so q is related to gamma by this relation. So of course we can define Liouville theory for any value of q and gamma, but you have to tune the value here this way for things to have the right conformal invariance. Okay, so there's another parameter mu which is strictly positive, but so mu strictly positive, the theory doesn't really depend on its value. The important parameter is gamma. Okay, and so what we did 7 years ago, is that we define this path integral using probability theory, and in a nutshell, so we took the squared gradient term. We said that, so if you take mu equals 0 here, q equals 0 here, then what is this thing? It's just a Gaussian free field on the complex plane, this path integral. But if you add the mu term and this linear term, well, you define your path integral by saying that it's the Gaussian free field with the Radon-Nikodym derivative, and this Radon-Nikodym derivative is nothing but the exponential of minus these two terms here. Okay, and so you have to define the exponential of the Gaussian free field, and this was done some time ago. And so what is the Gaussian free field? It's, so if you take a test function on C, so the one we're going to be working on today is that you say that the covariance of your field is nothing but the log of 1 over the distance between the points minus 1/4 of log of g of z minus 1/4 log of g of z prime. So yeah, okay. And so this is the Gaussian free field associated to my metric G. Okay, but I could work with other metrics, it doesn't really matter. And then once you have this, you have defined this Gaussian free field on your complex plane. So what you do is you set as the definition of your Gaussian measure, so the case Liouville mu equals 0, q equals 0, it's nothing but, okay, some constant times the Gaussian free field plus constant according to the Lebesgue measure. So this is this is the Gaussian free field we will work with, and you see it's kind of non-standard in the sense that usually people they work with a Gaussian free field, which is a probability measure, but the underlying one you have to use to define Liouville is one with an infinite measure, because the Lebesgue measure has infinite mass. So this measure, what is called the Liouville field, I mean the field which is behind Liouville conformal field theory, it is an infinite measure. Okay, so I mean it's very natural in some sense. It's like working with Brownian motion, but without prescribing the starting point. I mean, if you can work with Brownian motion starting from a point which you've sampled or according to Lebesgue, which is the invariant measure of Brownian motion. So, I mean, it's a way of preserving lots of symmetries. So once you have this thing, well, you can well construct your measure by splitting your action into two. So the first piece you get is the Gaussian free field I just defined, and then the second piece is going to be the Hadron-Nikodym derivative. And so to do that, you define the exponential of the Gaussian free field, and that's what Kahan did. And so how do you define this? You just regularize your Gaussian free field by setting a scale, a cutoff scale epsilon, and then so you modify your field at scale epsilon. This gives you a clean field, and then you renormalize the exponential by the average of the field. So since you have a Gaussian variable, the average of the exponential, it's the exponential of the variance over 2. And well, if you do this procedure, standard in physics, actually, it's called Vic normalization, then you get a meaningful limit only if gamma is between 0 and 2. And in which case you get a random volume form on your complex plane, which has finite mass almost surely. Now, let me say a word. I mean, in physics, they write Liouville for all gamma. So the point is that our approach to Liouville only works for gamma between 0 and 2. Because if you take gamma outside of 0, 2, if you try to construct this path integral, the exponential term goes to 0, and you're just working with Gaussian free field theory. So it doesn't work. So our entrance window to the Liouville theory, it's restricted to gamma between 0 and 2. And we don't know how to define outside of these values. Okay. And this is because you have this theorem on Gaussian multiplicative chaos theory. And then, okay, so I'm just writing the definition. So what is an average? So if I take a function of the Gaussian free field, say of a distribution. So since the Gaussian free field is in one negative sub-L space, if I take an average with respect to my Liouville path integral, then how do I define? Well, as I said, I say that it's constant plus my Gaussian free field, but I reweight space by the linear term. Now the linear term is just exponential minus 2qc because the field is constant on the curvature term, and I reweight by exponential the interaction term here. So this gives me a clean definition of the Liouville path integral. So it's nothing but Gaussian free field plus constant that I reweight by two completely explicit terms. One term which is a simple function in C, and the other one which is a more complicated function in C and my Gaussian free field. Okay, and then usually we like to work with something where we shift the field by minus 2q log of G. It amounts to working in a flat background metric and not the G metric. So, okay. Now, in this context, what are the correlation functions of the theory? So the correlation functions are kind of the Laplace cumulants of my Liouville field phi. So here I take alpha and R, but in physics they take alpha and C. I mean complex alpha, they're not afraid of that, but we're going to restrict to R here. So if I look at the exponential of my field at point Z times alpha, I'm going to call this a vertex operator. So this thing is not defined under with my previous definition, okay? Because the field is, I can define a function of my Gaussian free field, but only if it is something where like I integrate my field against a test function. Here I'm taking an exponential, which is not defined, right? So if you want to define the correlations of the theory, you have to once again use a regularization procedure. So you regularize your field phi to scale epsilon, you renormalize by something, and you go to the limit. And if you do this correctly, etc., you end up showing that, well, you can define, so based on a renormalization on these exponentials, and based on my previous definition of this Liouville path integral, you can define the correlations using probability theory, and they are non-trivial if and only if, okay, so gamma has to be in 0, 2, but once gamma is in 0, 2, they are non-trivial if and only if you have these conditions. The weights have to be smaller than capital Q, and the sum must be bigger than 2Q. And then you get something which has the right conformal covariance when you apply Möbius maps, and you know how, and you know the weights. Okay. So our correlation functions, they're well defined, and they satisfy, when I apply a Möbius, they satisfy this axiom here. The fact that when you apply Möbius, then you get the power of psi prime, where you get a weight, and the weight is explicit in terms of alpha and Q, where remember that Q is related to gamma by the special relation gamma over 2 plus 2 over gamma. Okay, so you get meaningful stuff, and more importantly, what you get is you get an explicit formula for these correlation functions. So I made a long story short, so you can show that the limit exists using these Gaussian free field definitions, and at the end, up to some terms which are completely explicit. Okay, this is a completely explicit function where S is so the theory depends on gamma and mu, right? And S is related to the alpha i's and gamma by this relation. So this is a completely explicit thing. So up to this first explicit thing, the correlation is nothing but the fractional moment, some power minus S, of my random measure, my random GMC measure, that I integrate against a function which has singularities around the point Zi's or Zk. Okay. Two different indices for Zi. And you see the conditions where it comes from is that if alpha I is too big, it's bigger than Q, it's bigger than gamma over 2 plus 2 over gamma, then this measure can't integrate the singularity anymore. And so this Z is infinity. And so you get something, you get a correlation at the end, it's 0, so it's not the right definition. And the other condition, the Seiberg bound, it's to ensure that, this moment here exists. So roughly, I mean, you see on the probabilistic side where these conditions come from. So the take-home message is that you get, once you've defined the exponential of the Gaussian free field, this random measure called GMC, Gaussian multiplicative chaos, correlation functions in Liouville, it's nothing but a fractional moment, or I think they call it a Meller transform, maybe in probability theory, of some random variable which corresponds to integrating the random measure against an explicit function which has singularities around the points. Okay, so we've defined this these things, and so now, we were faced, so this was like in 2014, and we were faced with this other construction in physics, as I said, the bootstrap. So in physics, the bootstrap, what they did is they postulated that for n equals 3, the 3-point correlation function was up to these explicit terms, roughly. It was nothing but it was an explicit formula, which was discovered independently by Dorn-Otto and the Zamolodchikov brothers. Okay, whoops. How come it came back to this? Weird. Okay, and so so the first thing we tried to prove with Antti and Rémi was that indeed we could recover this explicit formula. And so just to tell you that it took us 3 years to prove this formula. And when you look at it, I mean, okay, it's not completely obvious formula. So as I said, the structure constant, you can see it as the correlation where at point 0, 1, and infinity. So what we did is we showed that the probabilistic construction we have, it satisfies an explicit formula. And so this explicit formula is written down here. So you see it's very complicated formula, which involves here the gamma function, the standard gamma function, and especially, so alpha bar is sum of the alpha i's, and especially it's defined in terms of 4 upsilon functions. So upsilon is a function which depends on gamma, and when you take it at a point z, so here's the log of upsilon, it's some special formula here. And so this is defined for a region, and then you can analytically continue it in the complex plane. It has no poles, but it has lots of zeros. So this kind of very explicit function called Zamolodchikov's upsilon function. Well, you see, if you have this kind of crazy formula, and what we showed is that the fractional moment we have, which is our definition, it coincides with this thing. So this is ancient stuff. We did this 4 years ago. And so now we're doing the sequel. And so the sequel is the...
Maybe I have a question here. When you started to define your stuff, you introduced a G, which is not the usual metric on the sphere. But from what I understood, it was just to say, okay, we can take any G that satisfies some property. So here, this formula, it does not depend on G, provided that it's, I don't know, continuous and decays like Z4 at infinity, or there is something.
No, it's like the, you know, it's it will, okay, if you put a different G, then okay, if I say my correlations, I put a different G, okay, it's then the 3-point correlation is going to be 1/2 of DOZZ times a factor which depends on G, but which is completely explicit and called the Veil anomaly.
Okay.
And we wrote a generalization of that in the Mabuchi paper. Okay. So the dependence on G, of course it depends on G, but in a completely explicit way.
Okay, so this formula it's for GZ equal 1/1 plus Z squared to the square, or the one you say, which is, I don't know, max Z1
no,
to
it's
the
for
fourth.
1/Z to the power 4. I think.
Okay.
Like this one here, and if I take the round metric, I'm going to get some other constant in front.
Okay.
Like 2 to some, or 4. I mean, what you have to take home is that when you change G, you just multiply by exponential of a gradient of the conformal factor plus a curvature term, which is completely explicit. Okay. But of course, I mean, what I'm saying is that the theory doesn't depend on G. That's what physicists will say. Well, they call this a line bundle, you know, because if you change your conformal factor, then you know what happens, how the function moves. Okay. I grew. Now here's the. So you thought the first slide was painful. Here's a painful slide. So this is what we did in 2020. So I take gamma and 0, 2. Of course, otherwise, in probability, we have nothing to say on Liouville. I mean, we don't know. We take alpha I smaller than Q, and we suppose that alpha 1 plus alpha 2 is bigger than Q, alpha 3 and plus alpha 4 is bigger than Q. Then we get that if I take a 4-point correlation function at point 0, Z, 1, infinity, so you can always restrict to this case, because, you know, when you have 4 points with Möbius, you only have 1 degree of freedom. Because with the Möbius transform, you can always send your points to 0, Z, which is the free parameter, 1 and infinity. Now in this case, what you get is that if you write properly this OPE stuff I talked about in the very beginning, you get that the bootstrap construction says that the 4-point correlation function is some kind of constant times the 3-point correlation function, the DOZZ. So taken at points alpha 1, alpha 2, Q minus IP. So P is the integrating variable, times the 3-point correlation function, alpha 3, alpha 4, Q plus IP, times some power of Z, times some special holomorphic functions called conformal blocks. So this formula, so the right-hand side is what the bootstrap says on Liouville, and the left-hand side is our probabilistic construction. So our theorem is both coincide. Now, the problem is I can really not give you in 5 minutes a definition of a conformal block, which corresponds to these OPEs I talked about, but because it's written in physics as an infinite sum, it's holomorphic in around 0, so it's an infinite sum, and the coefficients beta n they involve combinatorics of Young diagrams and representations of the Virasoro algebra. So to prove this theorem, you really have to map probability theory to representation theory. And just to give you a flavor of the difficulty in this business, is that in passing, as a byproduct of our proof, we prove that this integral on the right-hand side converges, and that for almost all P, this holomorphic function, it has a radius of convergence equal to 1. Which would you expect from this expression? I mean, if modulus of Z is smaller than 1, then for almost all P, this holomorphic function, it converges. Now, so lots of people have worked on these functions in representation theory, and there's been a series of work which have been, have got a lot of attention. Is that in physics there's a conjecture which says that there is an explicit expression for these conformal blocks, and this was more or less proved by in a series of papers, 2 independent works by Maulik Okunkov and by Schiffman-Vassereau in 2012. But in these works, they're not, and I asked all of them, they don't know how to prove that that this power series here, so beta n has a combinatorial and representation theory expression, but they don't even know how to show that the conformal blocks that appear in physics, they have a radius of convergence, say epsilon for epsilon small. It's, I mean, even for a small epsilon, they don't know how to. So it's a formal power series. Z is seen as a formal. So probability theory gives us convergence of conformal blocks for free. So that's a nice aspect of probability theory. And let me say that there's an ongoing project which I find very interesting, and which is that roughly, I mean, what I explained to you the previous 20 minutes is that we derived probabilistic expressions of Liouville correlation functions using Gaussian multiplicative chaos theory. And an open question which they settled on the torus, so Gozal, Remy, Sun, and Sun, is that you also have a beautiful, I mean, probabilistic representation of the conformal blocks. So they're able on the torus, so they're different blocks, but because we're working here on the Riemann sphere, but on the torus, there's same kind of blocks, and they can show that it's the expectation, the fractional moment of a Gaussian multiplicative chaos type variable also. And so they're trying to extend their result on the sphere, and hopefully, so this is, I think, beautiful because, I mean, we're getting probabilistic representations of all these objects which come from representation theory. Okay, so I don't have much time here, but, just to say the blocks, as I said, I'm not going to go into the details, but they're non-explicit, and then they involve sums over pairs of Young diagrams with same size and special weights and inverse of scalar products, so called the Shapovalov matrix. But okay, I don't have that much time to go into the details. But here I have 4 minutes, 5 minutes, and I'm going to go in the strategy of the proof roughly. So roughly the strategy is the following: is that you see you have a 4-point correlation function, and you try to write it as a scalar product of 2 vectors. Okay, and then so you try to say that it's U scalar V in some kind of Hilbert space, and then well you find a special basis, and you know that if you have a basis in a Hilbert space, you know how to write U scalar V, right? It's the sum of UIVI where you've decomposed in your Hilbert along your basis. So the idea is to introduce a Hilbert space and to write your 4-point correlation function as a scalar product in your Hilbert space. And what you do is you introduce your Gaussian free field on the circle. So that's your Hilbert space plus a constant. So you take the Gaussian free field phi on your circle, okay? The simple logarithmic field on the circle. And so you look at your Gaussian free field plus a constant that you sample according to Lebesgue, which is not, I mean, this is because of our definition of our Gaussian free field previously. And so the key decomposition is that when you, I'm going to make a story short, but when you have your Gaussian free field plus constant according to Lebesgue on your Riemann sphere, well, you can see that the Gaussian free field, it's the harmonic extension of the logarithmically correlated field on the circle, plus what? An independent Dirichlet Gaussian free field in the disk, and an independent Dirichlet Gaussian free field outside the disk. So it's not very hard to show that the Gaussian free field we considered on the Riemann sphere, it's 2 independent guys which are, symmetry, which are related via this symmetry. You just do Z 1 over Z bar, you get the same field, plus harmonic extension. So you see we had some kind of moment when we defined our 4-point correlation function. We had a moment with respect, so we were averaging with respect to Lebesgue plus Gaussian free field. Well, what we do is we condition on the constant according to Lebesgue, and we condition on our log correlated field phi, and we average on the Dirichlet fields. And if you do that exploiting symmetries, you can show that the 4-point correlation function, it's a scalar product in my Hilbert space of 2 vectors, okay? Of 2 functions of C and of the logarithmically correlated field on the circle. And these functions are explicit, and they just correspond to cutting my interaction term into 2 pieces, etc. So it's a function of the field and of the constant and of my. So here it's you see it's harmonic extension of phi and Z1 and Z2, etc. And then you take expectation with respect to the Dirichlet field. So this means I'm conditioning on the value of my field on the circle. Okay, so you're able to write this. And then what you do is that then you do, as I said, then you do a spectral resolution. So what you do is that it's a scalar product in a Hilbert space. So what you do is you find a basis. And physics tells you that there's a very natural basis in my Hilbert space. And roughly, it has, this base is going to depend on Young diagrams, on couples of Young diagrams, and on a spectral parameter P. And this basis will have this kind of scalar product. It's going to be a Dirac mass, so it has a component which is exactly like a Fourier transform. So you should see this as a generalization of the Plancherel formula, times scalar products, which depend on P and on my Young tableau here. And so you see, when you decompose on this basis, it's not an orthonormal basis, so it's a bit of a complicated thing, because in that case, it's not so simple, because you have to take the inverse of the scalar product matrix. Okay, and then, okay, using conformal symmetry of our system, we're able to compute explicitly these scalar products between our vectors and these generalized states, these eigenbases, and summing the whole thing up at the end, we get we get that this infinite sum is equal to what they see in physics. So it's a bit frustrating because I can't really explain what is involved behind this thing, but to say maybe a few fancy words, how do you construct these bases? Well, you introduce random operators on my Hilbert space H, which are representations of the Virasoro algebra, and you construct these states by iterating these what are called the LNs, and you can see that there's lots of special symmetry, and at the end you're able to compute scalar products. So what we do is we take home message is that we construct using probability theory, we construct a Hilbert space. On this Hilbert space, we consider an infinite number of operators which satisfy commutation relations, which are called the Virasoro commutation relations, and we construct a basis by iterating these operators. And this spans the whole space, and we can construct the scalar products of these operators with respect to themselves, or with respect to these with respect to these vectors that we have here, which are both the ones where we take the scalar, where the scalar product of the vectors of which gives you the 4-point correlation function. So this is very fast and sketchy, and behind this there's lots of things. I mean, these vectors are in fact the eigenvectors of a natural Hamiltonian, which is a generalization of the so-called Liouville equation. So it's an infinite dimensional version of the Liouville equation, and so it's okay. And it comes this operator also comes naturally out of our construction. So I'm not going to say more. I don't have enough time. So there's lots of spectral theorems behind these guys. So I think I'm going to stop in a minute, just talk about perspectives, and maybe if you have more questions on the proof, I'd be happy to answer. But with the time required, I don't think I could go much deeper into the proof. So what I explained to you is that we have constructed, essentially an eigenbasis on a Hilbert space, and thanks to that, now when we have correlation functions, we can write them as scalar products on this Hilbert space, and then by decomposing these scalar products on this basis, we're able to compute compute these correlations in a different manner, and this yields exactly the bootstrap construction. Now, so I did this for 4 points on the sphere, and what we're doing right now is that using what is called Siga's axioms that we've proved on higher genus Liouville, we're able to set forth a generalization to higher genus surfaces of this idea for the 4-point correlation function. And so we're proving bootstrap formulas for Liouville on the torus and on higher genus surfaces. So this is going to appear on arXiv soon. And then there's these 2 projects I'm very interested in, but I'm not directly working on, is around Liouville. Is, as I said, Gozal, Remy, Sun hope they're going to find probabilistic formulas for the conformal blocks on the sphere. Right now they have the torus, and then maybe they can find, that would be a really fantastic thing. Maybe they can find probabilistic formulas for blocks on higher genus surfaces. And then there's this new program which has been on for a year, and which I think is very, very interesting. So based on our proof of the DOZZ formula and on our bootstrap program for Liouville, so Sun and Ong have initiated a program which could be summarized as construct recover the bootstrap construction of CLE. And of course, this is what is difficult is that even in physics, there is no bootstrap construction of CLE. It's still kind of, so it's a very hot topic, but what in physics, like people like Seller or Jacobson are working on that. But what they do know in physics, or what they predicted, is that you can construct some kind of 3-point correlation function out of CLE, and that you should recover a variant of the DOZZ formula. And a few months ago, that Ong and Sun put that on arXiv, they were able to show that when you construct 3-point correlation functions out of CLE, they do satisfy this variant of the DOZZ formula. So this would correspond to taking gamma purely imaginary, and the whole discussion I did, but unfortunately we do not have a, so this is a CLE construction, but it would be interesting to have a path integral construction of these objects. So right now these objects are constructed in probability theory using CLE. Okay, and then there are lots of other projects that also Hubert has been involved in, which is now we're trying to look at kind of different path integrals where you have instead of exponential, you take exponential phi plus exponential minus phi, and so according to which gamma is imaginary or not, you have the sine hyperbolic model or the sine Gordon model, and one can also ask if you can define the objects and recover formulas from physics. Okay, so thank you for listening. I'm done. Thanks a lot.
Thank you, Vincent. So yes, who would like to ask a question? I think you can unmute yourself directly or raise your hand as you prefer.
Yeah, don't hesitate. I mean, yeah.
Okay, so I will start the question session. So your 4-point formula, you say that it's valid for z smaller than 1 in modulus, but do you have this symmetry with z smaller than 1, z larger than 1 that gives you the formula on the whole sphere, or?
Yes. I mean, yeah, because what you do is if you have zero, no, I mean if you have 0 z larger than 1 infinity, it's the same thing up to some power d.
This is what I imagine, but okay.
Yeah, no, I mean it's very general because
so there is no restriction. It's not that
no,
you have
there's no restriction here. No, because the thing is, by conformal symmetry, you map it to this case.
Okay, and there is something that I wanted to know about the first step of the proof when you're taking this circle and you're conditioning to it. So you have 4 points, right? So what does that? What does this? Well, is it important where you place the circle, and what is? I mean, why is the position of the unit circle is good when you consider these 4 points?
It's a good question. It's not. It's just that it's handy, but you could do it along. In fact, you can do that. It's called. I mean, in some sense, we do it in a more intrinsic manner in the Seagal paper that we're doing. I mean, you can cut your surface along what you want and reglue. This is just a regluing of the Riemann sphere along the circle, but you can glue differently, and you'll get other blocks, but essentially all this should lead to the same thing. So
okay.
There's an intrinsic.
I don't know. Here you have 2 points on one side, 1 point on the other side, and 1 point just on the circle. If I understand well.
No, you. Yeah. It's
Is
true.
Is it important to have 1 point on the circle, or?
No, not at all. No.
Not at all. And it's important that it separates. I mean, maybe you don't want to have the 4 points on the same side, or not even that.
Well, it depends. I mean, if you have the 4 points on the same side, what you're going to do is you're going to cut on a smaller circle, and you're going to get the same kind of result. I mean, there's no. I mean, What does it mean being on the same side? It's this circle.
No. I mean, for your proof to work, you will choose your circles so that they are not on the same side. This is what I wanted to know.
Yeah.
This was important.
You want to take 2 points in one circle and 2 points outside.
Okay. And here you have 1 point on the circle, but it's not.
In fact, we prove it. We don't take 1. We take Z prime bigger than 1.
Okay, so that you have 2 and 2.
So you have 2 really distinct guys, and then at the end you make Z prime go to. Then at the end, what you do is that you can scale. I mean, if you have Z prime, you can apply a conformal map, and it's the same thing as Z over Z prime 1 infinity. I mean, you can play around with conformal invariance. You should really have in mind that you prove it for 2 points inside and 2 points outside.
Okay. Yeah, this is
the important point is that you glue your surface, so you cut it into 2, and you put your points inside, and you put the other points outside.
Okay. Oh, there are things in the chat. Okay, so maybe I will read, but Julian, if you want, you can unmute yourself and speak.
So when you spoke about the 2-point correlations at the beginning, you said that the physicists had to guess this constant.
I can't hear you very well.
Can you pump up the volume of your microphone?
I will try. 1 second.
Oh, Vincent,
so you're talking about is it your question about the complex constant?
Yes, exactly.
Okay. So no, so it's called DOZZ. So the story goes this way. In 1984, BPZ, Belavin-Polyakov-Zamolodchikov, they derived the bootstrap construction of conformal field theory, but they wanted to construct Liouville, and so they weren't able because they had to guess this 3-point correlation function that you put in your recursive procedure. Okay, so the 3-point correlation function is what you put here in your bootstrap, and they were unable to guess what formula they have to put here for the construction of the theory. And it's only in 1994, 95, 96, around these times, that Dorn-Otto and Zamolodchikov, they guessed the formula that I wrote here, C DOZZ gamma mu, and they called it the DOZZ proposal. And so they said, I'm going to use it for a bootstrap construction, and it seems to give something meaningful. So, but their guess was very ingenious, but non-rigorous.
Okay, thank you.
And are there any elements of the guess that are related to elements of your proof? I mean, it's difficult to know, but
no, because they do an analytic continuation on a finite number, essentially. They compute moments, and they have a finite number of moments, and then they say, okay, I'm going to analytically continue it. So their guess is related to the path integral, but we cannot exploit at all their guess to give a proof. Our proof is related. I mean, it's really highly related to another of a trick in physics called the Teschner trick, and but it's a very, very long story. But from physics, a very important input of our proof is to implement rigorously what is called Teschner's trick, but not at all the DOZZ way of doing it. I mean, Teschner re-derived the DOZZ formula using another approach, some kind of axiomatic approach that somehow we could follow using probability theory.
Okay, thanks. Do we have more questions for Vincent? Okay, so I think thank you again, Vincent. It was a nice talk. And yeah, I hope we can see you back in Rio someday. So you gave the talk in your last visit. I remembered probably incorrectly that Remy was giving the talk last time. But
I thought I gave a talk on DOZZ last time.
Okay.
But no, we never talked about the Bootstrap, right?
No. It was a talk on DOZZ, but yeah, okay.
It was me, I remember.
Okay.
We were. Ouais, non, je m'en souviens.
Okay.
Okay.
So I guess, yeah, we will meet next week for the next seminar. So see you everybody, and thank you again, Vincent.
Merci. Bye bye.
Ciao.